Que graben ustedes también.
Sí, yo estoy grabando, sí.
Right, what can I arrancar?
Yes.
So, I'm going to screen share now the presentation we have for you. And
Okay.
there we go. Let us know is
Okay.
right.
Sound
Ready to get going?
is working? Yeah. Julian? Yeah. Okay. So, I don't see my face. Well, hi. I'm Sham. I'm Juan. I'm the one who was mailing with you.
Okay.
So, well, we will be. Okay. Wait a second. We have. Yeah. There we are. So we will be doing this short PowerPoint presentation just for structure this thing. So yeah, we are, as you may know, we are the digital rocket team. We are from Argentina, and we'll be competing in the 10K SRAD hybrid category. Well, this is our
Yeah.
Okay.
Okay.
Well, this is our second year participating in the Spaceport America Cup. It's our first year with the hybrid engine. And well, our experience is canceled competition some years ago, and well, last Spaceport America Cup. And well, we have obviously our flag of record that is Jasper Barnett, and we have a series of advisors and people who help us from ASEMA, that is the Argentine Association for Modern Rocketry, and obviously people from the university. So in general terms, the team is organized in 4 big sub-teams. We are organized in a functional way, mainly a subsystem division, namely propulsion, avionics and recovery, aerostructures, and aerodynamics. And we also have a media team that does all these things with the sponsors and the university social media. So the mission is quite a standard Space for America mission. We have a modernization, a boost phase, a ghost phase. This year we will be trying to implement an air brake to work in the ghost phase. Then we have a single deployment, dual parachute recovery system. And after that, obviously, we have the touchdown. So this is the general view, the overview of our vehicle. It is divided in 7 main bays or sections, namely the nose cone, the recovery bay, avionics bay, the air brake, the oxidizer tank, the ball bay, and the motor bay. Is very similar to the way we subdivide the rocket the last year, and as it works quite right, we're trying to repeat that things that worked.
Okay.
So now we'll be presenting the aerodynamics part. We'll be starting with that. So here is Axel, who is the
Hi. I'm the leader of the aerodynamics and flight dynamics team. I'm gonna, first of all, as a simulation software, we used RocketPy. It's an alternative to OpenRocket. It's an open source software written in Python. It allows us for a lot of manual things to do. We can input our own drag coefficients. We can simulate control system for the air brake, for the parachutes, and yeah, we use this to achieve right now a predicted apogee of 12,000 feet. This is without air brake correction and is subject to change a bit closer to launch. We can fine tune this a little bit more with extra mass. The max velocity reached is of 900 feet per second, and acceleration is 9.1 g. Our peak thrust is at almost 9,000 pounds, and lift of weight is 87 pounds. In terms of stability margin, we aim for a stability of 1.6 at liftoff, and then this grows as mass reduces, and the center of mass varies in position to a maximum of 2.4 to aim not to be overstable. This is almost the same as what we had last year, and in terms of flight and stability, it worked pretty well. So we didn't change much there. Um, we have a radial departure speed of 110 feet per second with a 26 feet long rail. In terms of environment, in Rocket Pi, we can do a reanalysis of environment and also predictions. And we did a reanalysis of the last 20 years of spaceports, American Cups, and used the average of this to design the rocket and, and do all the simulations. Later on, when we are closer to launch date, we're going to use GFS forecasts to input into our model.
Okay.
Well, now about the aerostructures part of the rocket. So the main aerostructural parts of the fuselage are well, obviously the cans, the body tubes, which are comprised of the fin can, the electronics can, and the parachute can. The nose cone, as we have hybrid propulsion this year, we have developed a composite overwrap pressure vessel, which we have noted as COPV. We have columns, which we will explain later on. Obviously, the fins, and this year we implemented a bow tail. So the main focus is the minimum diameter while ensuring payload fitting. So this is us trying to make the rocket as slim as possible while still being able to fit all the payload and subsystems into the rocket. The minimum length as well, in order to keep it short and stable. Thickness of the body tubes, taking into consideration all the loads experienced during flight, were all evaluated and verified using finite element analysis, and the shape is optimized for aerodynamics. So here is just a clear layout of the whole structural parts. About the body tubes. So it's three main body tubes. They're made out of wound fiberglass, which we wound ourselves here in our school, since those machines are not commercially available, at least here in our region. So obviously the fin can is the longest one, followed by the recovery can, and lastly the electronics can. All tubes of the fuselage are 6 inches in diameter as an inner diameter and 6.18 as outer diameter. And what the length is specified here on screen. We also have pressure relief holes and rail buttons on the fin can in order to guide the rocket through the launch rail. So this is just a couple of pictures. We used an X winder, which several teams have as well. But in America, we do have one available here, but we have quite perfected the process of winding and the whole structure of the machine. And just a couple of pictures. About the nose cone. So it's optimized for two main things, which is subsonic flight and max inner volume. Since we have to fit the payload into the nose cone, we aim to make it as short as possible, while still keeping sufficient space to keep the payload within the rocket. This, as a difference compared to the other tubes, we laminate with glass fiber, using just traditional hand lamination techniques. And this whole nose cone is tipped by this aluminum tip, which is as well here specified on screen. So these just a couple of pictures about the lamination process. We used a male mold this time as compared to a female mold for the past year. Just traditional fiberglass wet layup system using vacuum bagging in order to keep the compression onto the molds good and the resin fiber ratio to as good as possible. So yeah, about the fins, we have 4 trapezoidal fins as well with all the measures specified here. It's always a trade-off between stability and fin flutter. So we can go bigger, be more stable, but be more prone to fin flutter, which is a problem. Or we can go smaller, be a bit less stable, but have far less probability of fin flutter. So it's always a trade-off we're trying to make. These, as compared to the rest of the aerostructures, are made out of carbon fiber in order to get more rigidity and reduce the probability of fin flutter. They have all beveled edges and are secured. Well, they are glued onto the body and then secured using a tip-to-tip laminator.
So that would be a reinforcement going from tip to tip from every fin on the four faces, which are going to be reinforced in order to make sure that the rigidity is really there. And the most important part about the geometry of the fin is that the root short to span ratio, which would be this 8.66 inches of the base to the 4.33 inches of the height, is always at 2. And the general thickness is 0.14 inches. So we try to keep it as even as possible throughout the laminate. So this is a flat laminate. We used, as well as I said before, carbon fiber using traditional hand lamination, vacuum bagging, epoxy resin. Um, and here's kind of a bit like the star of the show in terms of air structures, which we have designed, which is this COPV composite pressure vessel. Um, we have seen many pressure vessels made only of aluminum, but this one we decided to reinforce using glass fibers. So we have developed round tubes for the PASS rocket. We had quite a bit of experience winding these tubes, and we decided to do that for this year. So it's a hybrid engine. This is the nitrous oxide tank. It's lightweight, or at least as most as we can. The main goals of it is to maintain its integrity under the structural loads of the rocket during flight and ground operations. That would be transportation, charging of the pressure vessel and everything, and obviously the flight loads. We also designed it to keep it as easy to assemble and disassemble as possible in order to make it easy to clean and integrate into the rest of the rocket. We're going to show that in a minute. We have a operational pressure of 70 bar, and as per the regulations, which ESHRA demands, the safety factor in terms for stool-developed COPVs is 3, and we did ourselves a hydraulic test at 1.5 times the operating pressure for at least twice the time we're going to expect the rocket be on the pad loaded, like for the full duration of the flight and ground operations. The volume is 11 liters, and it's also verified using finite element analysis. These are a couple of pictures of the COPV. So it's just a tube, but it's got an inner lining of aluminum, which is 1.7 mils thick. It's 149 millimeters long, and it's wound on the outside using glass fiber tow and epoxy resin as well, just like the fuselage, the only difference being the angles we're winding on. Uh, and also the thickness, it's also 7 millimeters, so it's quite a bit thicker. We have for the lids, we have lids which slide from the top and bottom onto the tube, and they are secured using radial bolts. It's actually 15 M10 bolts, which we've tested up to 1.5 times the operating pressure, and absolutely no issues with that. The bulkheads, which we call the lids, are 6061 aluminum CNC machine in house, and are on the inner side are semi-elliptical in order to house the complete volume and be more efficient. On the right side is the complete pressure vessel. On the left side, there's a picture of the static test we did with the 1.5 times operating pressure. So now on for the air brake, back to Axel.
Yeah. The thing we wanted to do with the air brake is have a control over our apogee. So the solution we came up with, and a lot of other teams too as well, is an actuation with a servo and actuating um, four plates that go in and out of the body frame to increase our drag and have a air brake. Yeah. So what we did is, first of all, we needed to know, at least estimate the drag coefficients for the air brake, for the rocket with and without air brake. To do this, we did CFD simulations, which we validated with our previous year's rocket, 03. And we also compared them here on the right. There's a graph of CD versus Mach number. We plotted the coefficients we got and the coefficients given by Aerolab and Rasa Aero, which are two programs we can use to get drag coefficients, which are pretty reliable. And on the left side, we have our area control map, which is what the computer is going to use during the flight to determine if we need to open or close the air brake. How this works is With Rocket Pi, we got um, a few position curves plotting instant velocity and altitude that would reach a certain apogee. So we have the final apogee of 10,000 feet, and then plus 10% and plus 20%. And the idea is that if the rocket is under certain conditions, we defined it as motor has to be shut off already, Mach number has to be below zero point 0.5, amongst a few others, and is at the same time above one of these curves, then the air brake should deploy. And we have many, here in this case, right now we are using three curves to kind of scale towards the apogee we desire, to not undershoot the apogee because we didn't account for something. And then, yeah, basically we go even closer to the apogee every time. And so the air brake deploys, then shuts off, and deploys again, and until it reaches the apogee.
Well, now for the coupling devices, this year we used basically the same coupling joints and bulkheads we used last year. So those are flight-proven parts, so we're quite comfortable using those and making those again. So we have these field joints, which we call the tubes, which slide into the fin can, electronics can, or parachute can, and the bulkhead, which is a part which holds them together. They're bolted together from the outside. So we have two kind of field joints. These two are extruded 6005 aluminum, which we simply cut and bored the holes in. It's 5 glued to the fuselage, which are the shortened ones, and one which is a sliding fit for ejection. So that's about it for field joints. Really simple, flight-proven design. We're quite comfortable flying with that. In terms of bulkheads, we have different kinds of bulkheads, which are coupling the different parts of the rocket. We have the motor bulkhead, which basically couples the fin can to a valve space or valve can, which we have in order to make the link between the actual engine casing and the composite pressure vessel. The electronics bulkhead and the payload bulkhead. Both the geometries and all the holes in them are in order to accommodate for set parts. Everything is machined 6061 T6 aluminum as a standard on CNC lathes and mills, which we have here in our shop. A couple of pictures of that. This is the geometry we're talking about. It's like if you look at it from a side profile, it would be looking like an H. So we have these sliding joints which are glued onto the body tubes, are bolted then onto the bulkheads. So this would be a accurate representation of everything. The force is transmitted through the bolts, a shear force, and everything has a safety factor of 2. Again, we have flown this before and we had no issues with that. About the electronics bay. So this would be the electronics bay. So you can see it's coupled onto the electronics bulkhead from above, and it's held by the electronics plate from below. The bulkhead would be obviously aluminum. The electronic plate is currently plastic, and everything electronics is housed within that space. The bulkhead on the other side, as a structural part, also serves to hold the mounting point for the ejection wells and U-bolt. That would be the bulkhead on the right side of the electronics bay, which is pictured. And the electronic sled, which is the part on which the electronics goes mounted to, is mounted on the thread rods. It's 4 threaded rods and are fixed in place by nuts on one end. And this whole assembly also houses the boxes for the pull pins and computer switches. In terms of payload bay, so I've talked before about the nose cone being optimized for space, and so that would be what goes inside the payload bay. It is mounted onto the payload bulkhead, which would be the uppermost bulkhead within the rocket, using M5 screws. The main parachute line connected to the bulkhead by a U-bolt. So the U-bolt is mounted on the underside of the bulkhead. On the upper side, we have the payload. The key characteristics here are that the payload is 3D printed. It is secured to the bulkhead with bolts. So we have a sliding weight which is fixed using bolts, which we can slide within the payload in order to move the center of mass. That's all in order to ensure flight stability. And we also have a housing for a GoPro to capture flight video during flight. So that will be everything about payload bay. The motor bulkhead is the undermost bulkhead within the rocket. The uppermost part of the rocket motor casing is touching against the motor bulkhead. And from the motor bulkhead are three rods, which are then making contact with the pressure vessel. And this bulkhead is responsible for transferring the thrust from the motor onto the rest of the structure. It's a crucial part, and yeah, very similar design to what we have already flown. So the valve bay, which I've mentioned before, is the space which is between the engine and the COPV pressure vessel. So this is where all the valves go and where these rods are also housed. So the motor bulkhead would be on the lower side and the pressure vessel on the upper side. And this is the structure which transmit the thrust from the motor bulkhead onto the upper part of the structure. These are two aluminum 6061 rings, which we can see here, and three 6061 columns. Yeah, about the valve bay. So, and this is obviously a space which houses all the valves and everything regarding that. Now on to propulsion.
Yeah. Well, so thank you. Sorry. Yeah. So under the propulsion part, as you may know, we are developing a hybrid rocket motor. We develop hybrid rocket motor. Yeah. Throughout the development, we go through various phases that started with the ballistic simulations of the motor and what we wanted to achieve with the rocket, with the motor performance. Obviously, before that, we select the propellants. And with these two things, we kind of set the requirements for all the mechanical parts that are part of the engine. We also take into account all the thermal loads present in the motor, and we also then test the ignition sequence, and obviously we statify the engine. So, as I said before, we start selecting the propellants that are paraffin and nitrous oxide, mainly because of Spaceport America Cup regulations and because of the availability of both oxidizers and propellant. The initial design or the performance parameters were set by an iterative design process with the aerodynamic team, mainly because we wanted to set the motor mechanical parameters and ballistic parameters to achieve a specific apogee and a specific and stay below the transonic regime. So that was what we were looking for, and the motor tries to adapt to that requirements. Um, we also size the motor so it has more impulse than what is actually needed, mainly because we're counting on combustion instabilities and combustion inefficiencies, and also because we are planning to use an air brake, so it is better to be above apogee than below the target apogee. Um, yeah. So we are using nitrous oxide, mainly because it's the only oxidizer that we can use for Spaceport America Cup, but also because it's self-pressurizing and it has a series of advantages, especially in the context that we are. I mean, it is available in Argentina. It's something pretty safe to use in a university environment. So it was like the logic decision. Um, and we're using paraffin as our or paraffin-based fuel, mainly because in Argentina we don't have access to HTPB or PMMA or more classical hybrid propellants. Um, it has its drawbacks, especially when talking about the mechanical performance of the fuel. But we thought that it was easier to address these strength problems with additives and with some on with a structural approach to the grain than trying to get our hands on HTTP or something like that. That is very difficult to obtain here in South America.
Yep.
So the internal ballistic of the rocket were simulated with HRAP, that is Hybrid Rocket Analysis Program. I think it's very common simulation software for hybrid rockets. And well, as you may know, we use it. We, the we inserted the parameters. We make an iterative process of varying the parameters to achieve the performance value that we wanted. We go with the hollow cylindrical grain because we thought that it will be easier for us to develop that kind of grain. And we have some requirements that we get from experience of other universities, from, for example, the Terra team from Delft in the Netherlands, and other advanced hybrid teams, mainly to avoid ignition problems and combustion instabilities. So we go for, or we set that our oxidation to flow ratio to be less than 15, and our oxidation max flux to be less than 600 kilograms per meters per second in every moment of the burn. So for our paraffin grain, to address these the structural problems of paraffin, we use a structural grain approach. We call it like that. Is the idea behind it is to add a 3D printed structure to the grain to maximize or to enhance the structural properties of the grain. So in our case, we use shadow the structure, which is a structure that has a lot of surface area with very little volume. So we 3D print in ABS this structure, and then we pour paraffin inside this structure. So the grain now has not only the little the strength that paraffin has, but also have the structural support of this ABS structure. We also add the stearic acid. We add 10% by mass of stearic acid to the paraffin to make it stronger and to higher a little bit the melting point. And we also use black candle dye just to make it darker so we can avoid problems with radiation melting the grain inside the combustion chamber. So this is a kind of an overview of the motor. Um, as you can see, it has a pretty big, or it has a post-combustion chamber and a pre-combustion chamber, mainly because of we were kind of afraid of combustion instabilities and combustion efficiency, so we just kind of stayed into the conservative side with this post and pre-combustion chamber. Um, so the casing is designed to be easy to assemble. Last year we have kind of a little, we had some problems with motor assembly. It was our first time in the US, so we had our hands on a COTS motor, and we kind of copied the approach that solid cut motor has in the assembly of the motor. So the forward closure is the injector plate, is where the injector is placed, and is bolted to the casing. But the nozzle is supported by the nozzle retainer that is a threaded ring, um, which make the assembly process much easier. So well, all the casing and all these parts were designed with the maximum operating pressure and the safety, um, the factor of safety that we set for the whole motor, that was 1.5 and 2 for some critical parts like the thread. Uh, and the main operating pressure was the one that we get from the ballistic simulation. Um, yeah. Okay. Then the nozzle was designed was optimized, or is a thrust optimized parabolic nozzle, mainly because we were looking for shorter nozzles and high efficiency nozzles. Since now we came from solid development last year, and this year that we have a real gas flowing through the nozzle and not a lot of solid little things. We just go for an optimized nozzle since it makes sense to optimize these kind of nozzles. So it was optimized, or the inlet and outlet conditions were get from the ballistic simulation and from NASA's Zero Run. Um, and we developed a little MATLAB program for the thermal analysis of the nozzle and for the draft optimized parabolic profile. Also, the nozzle um, was checked with finite element analysis. So the injector plate, with the injector, we went quite conservative. We are using a shower head injector, um, which is divided in two parts: in an injector bulkhead that is the forward closure of the motor casing, and also is the connection with the oxidizer tank, and the injector plate that is just a plate that bolts onto this injector bulkhead, and it's just a plate because we wanted it to be easy to change and to iterate on the injector design. So the injector boost, as I said, is the forward closure of the motor, and also is the anchoring point for the motor into the motor bulkhead. So it's the part that it transfers the load from the motor to the rest of the structure. And it houses the channel for the nitrous oxide to flow into the injector plate and into the motor. The injector plate, as I said, is a shower head injector. We use it, or we go with the smallest hose that we could made in our shop, mainly because we wanted to ensure a big pressure drop in the injector to avoid instabilities. Um, so yeah, and this injector valve was also checked, or was also designed using finite element analysis, since it's quite of a complex part. So this is a PID, or a diagram of the injection line. As you may see, we have the flight tank as the central part of the injection line. This is the PID from inside the rocket. So the flight tank has three main lines that go from the tank to the outside. That These are the fill line, that is the main line that injects oxidizer to the combustion chamber. It has a main bulb and a non-retort valve, or a check valve, to avoid downstream flow back from the combustion chamber. It has a filling line from which we use for filling the tank, and it has a vent line in the top of the tank where we have the vent valve and the parts disc that work as a safety measure for the flight tank. This is a kind of a summary of what I just have said. This is the part list of the field line. So the oxidizer tank in the from the propulsion team, we set some requirements for the tank for the aerostructure team to achieve, and that was mainly driven by the requirements from the engine performance. The tank volume was set to 11 liters with a 10% of fuelage. The working tank pressure was set to 70 bar, mainly because of the nature of nitrous oxide. And the fill line was set to 3/4 of an inch, a diameter of 3/4 of an inch, and the filling line, the line that fills the oxidizer tank, was said to be 3/8 of an inch. Mainly because we wanted to achieve this 30 minutes time cap for the tank filling, and the fill line to the motor is 3/4 because we wanted it to be as wide as possible for avoiding two-phase flows or any big pressure loss into the line. So in the venting line of the tank, we have, as I said, a vent bulb, which is a custom vent bulb. We designed this bulb because we didn't found a suitable bulb for that will be normally open and will withstand the pressures of nitrous oxide. So we designed this bulb that is a normal open bulb. When there is an energy failure in the rocket, this bulb is set to open mechanically with the with the tank pressure. Um, and it is commanded with servo, so it can be commanded on purpose from mission control. And as a safety measure, the operated tank has a burst six set to Raptor at 100 at 1500 psi. That is, uh, I think that is 20 bar, which is the design pressure of the tank. So in any case anything goes wrong, the buses will depressurize tanks. So thermal management, you want Gaspar? Sí.
Yes. Yes, so for the thermal management of the rocket, we chose to design and actually research a material. We did a series of tests following the ASTM E25 guidelines. The series of tests, the first one, we chose the fiber, which would go into the composite for making of the ablative. And the second test was to choose the additives for the thermal insulation. So this thermal insulation that we researched and designed is called SPGF because it's a sodium bicarbonate glass fiber reinforced epoxy, and the design of it is in the following page. Okay. So this is the design of the insulation. We have three cylinders which are connected with RTB silicone, which ensures high shear strength and thermal resistant interfaces. The outer cylinder or outer sleeve is called the thermal liner, has a thickness of 2 millimeters. And then we have two cylinders which connect at the pre-combustion and post-combustion chamber. Here, the thickness is increased in the pre-combustion because there is the mixing of the gases that creates a high heat flux to the walls, so there is additional thickness. And in the after mixing chamber, because we have all the developed gases of the combustion. Here in the right, you can see the thermal insulation, which was tested in the first and second test. There wasn't any visible regression, and the temperatures were in the ordinary range. So it was validated in the first and second test with no difficulties.
Okay. For the ignition of our motor, we used kind of a steel wool and black powder igniter. It's basically a piece of steel wool with black powder in it, and it has a pyrotechnic initiator. So this assembly is set just below the injector plate, and when set to fire, it just burns. The steel wool oxidizes and generates a lot of heat, and in this way we just lighted the motor. The ignition sequence that we were using, we tested, and it is, and as now is working awesomely. Um, is at t minus 4 seconds. We set the main bulb to bleed. That is to just let a little bit of nitrous oxide to flow into the combustion chamber. At t minus 3 seconds, we ignite this steel wool and black powder assembly. We let that to burn for 3 seconds, and at t minus zero, we command full throw to the main bulb. And in the test that we have done, it worked perfectly all the time. So we think that is kind of an effective way of igniting the engine. So in the ground side of the fueling system, we have, this is the PID, the diagram of the ground side. So we have two main control valves that have the main feeding bulb, that is a solenoid open close and normally closed bulb, and a vent bulb that is identically to the one that is mounted onto the rocket. So it is a normally open vent bulb for safety reasons. This whole assembly is monitored from mission control through uh, digital pressure gauges and and temperature sensors in the line. Uh, and the safety measures that this system has as are a relief bulb, a commercially available relief bulb, a vent bulb, as I said before, a manual despressurization valve as the last resource, and it has also a bypass bulb that bypass the main filling line. So, and it's set up for assembly and disassembly procedures. Um, yeah, this whole system connects to the external tank that is a commercial tank, commercial cylinder of nitrous oxide, and it connects it connects to the rocket with a quick disconnect, which serves as the umbilical connection to the rocket. So the integration of the motor is, as Gaspar said before in the thermal insulation part, is made with we designed it to be easy to integrate. So all the thermal insulation and the grain are glue with RTB silicon. Um, in this way, we have like this full cartridge that then we can just insert into the engine. So we just insert all this cartridge into the casing. We close the casing with the forward closure, that is the injector bulkhead, and at the end we just put the nozzle in the front in the back part of the engine, and we thread the nozzle return ring. Well, the tank has this is like a diagram of how the feed lines exit the tank, and the whole system can be integrated outside the rocket. So all the propulsion system is integrated and fully assembled outside the rocket, and then all the other rocket parts just assemble into the propulsion subsystem. So it's easier to assembly, and we don't have problems with aerodynamic parts um, getting into or making us having trouble with adjusting valves and ferrule connections. So we tested the rocket two times. We made two static fire tests. The first one was pretty successful. We have data, thrust data, and pressure data, which were not, I mean, they were not ideal, but they were very good, pretty good. Um, we suffer from combustion instabilities. It can be seen in the video. Is very it can be seen the combustion instability. It's not it wasn't a pre-violent instability, but it was there. And the main reason of that was that we were using a smaller line for feeding the engine, mainly because where we have the test stand that they have some kind of trouble, and well, we have to go with a smaller diameter line. And in the second test, well, this is the data that we have after filtering from thrust and pressure. Um, the second static test, just it was a fully assembled propulsion system static test. It was nominal time. It worked great. It looked great, but we don't have data because we have a problem in the acquisition system. So we think that I mean, analyzing the videos, it can be seen that the combustion was better. There was no instabilities. It was uh, a much cleaner combustion. But well, we don't have real data from this, so we think that the burning was nominal, mainly because of the time, the burning time. But we don't really have thrust and pressure data on this last test. So avionics and recovery, I think that is Pedro. Um,
Yeah, so hi Paul, I'm Pedro, I'm the avionics team lead. I'm going to explain how the avionics and recovery is part of the rocket. So you can go ahead with the slide. So the avionics was in charge of basically four main systems. We had the recovery system, which was in charge of bringing the rocket safely to the ground, the control of the motor and engine systems, the air brake, which was already explained, that we were in charge of controlling it and gathering telemetry data, and also the tracking, which was a standalone system based on a GPS. So if you can go ahead with the slides, you can see the main computers that we chose. Basically, we chose this because they were, for the first two cases, commercially available COTS computers. We have the GPS tracker. That's a GPS fairway tracker. We already used this one in the last year competition, so we know that it is reliable, and that's why we chose it. Also, it has all the functionality that we need. This allows us to get a real-time telemetry data from the rocket flight, and also it allows to locate the rocket once it's landed. For our recovery computers, we're going to use two redundant, according to competition guidelines, COTS computers. These are the chosen one were the RRC3 altimeters. We chose this because it basically has all the functionality that we need. It allows us to deploy a drogue and a main parachute, and also to set one of those in like a backup mode, so that in case the first computer doesn't deploy the drogue parachute, the second one is able to, with a certain delay. Also, these recovery computers allow us to gather telemetry data that we can recover after the flight has finished. For the engine computer, we chose an ESP32. This is basically because it's an Arduino platform, but with a much powerful processor. It has GPIO pins and allows the flexibility of Arduino programming and easy of development, but basically with a better microcontroller. In the next slide, I'm going to present what this computer exactly does. But finally, for the air brake or the controller of the air brake, we chose to develop an in-house, completely in-house board. It's also based on the ESP32, but it has integrated altimeter and barometer sensors to gather redundant telemetry data. You can go ahead with the slide. Okay, so this is a diagram of the onboard avionics systems that are located in the electronics eBay that was presented before. As you can see, the systems for the recovery are completely dependent of all the other systems inside the rockets. Each of the altimeters is powered by an independent 9-volt alkaline battery, which is by recommendation of the manufacturer, and each of those is connected with 2 igniters to the deployment charges and with 1 igniter to the line cutters. All of these systems are completely redundant. And then we have all the systems regarding with the GPS, the SRAD computer, and the OBEC. OBEC is what we call the onboard engine computer. So we can go ahead. Okay, going ahead with the recovery, we have an overview of what we designed. As you can see, it's a pretty standard, this is a little diagram, but it's a pretty standard system. We have a drogue parachute that deploys first. This allows us to stabilize the rocket and then deploy the main parachute to land it safely on the ground. We chose an aero-rigging 24-inch elliptical parachute for the drogue one, which is wrapped in a Nomex blanket for thermal insulation, and to be sure we don't have any problem with the pyrotechnic deployment charges. It also bolted down to the rocket to the eBay and fin can with a Kevlar cord rated for 1,200 pounds of force. We also chose for the main parachute an aero-rigging 8-feet high-performance parachute, also wrapped in a Nomex blanket, and that basically attaches to the same point in the rocket and also has the same Kevlar cord. Perfect. In order to deploy these parachutes, we designed 2 pyrotechnic deployment devices. The main one is the deployment charge. This is basically an aluminum machine can with a machine screw in order to unite it or bolt it into the bulkhead. This is filled with 2. We have to test the. We have problems here in Argentina sourcing good quality black powder, so we are using for now only 2 grams of gunpowder in our tests, which were successful. But we're going to have to retest this when we are in the USA because the US gunpowder is much better quality than what we can source here. So we have to empirically adjust that. So we also designed a line cutter. This is for the main parachute. This allows us to tie the main parachute inside the Nomex blanket and deploy it exactly when we want it. It just cuts the wire that holds this together and allows the main parachute to deploy. It's basically a circular blade with a small amount of gunpowder, which we'll also have to empirically correct when we're in the USA, and 1 igniter. Something very important for this, the deployment charges will be wired with two igniters to each computer in order to ensure maximum reliability. The line cutter, because of a size constraint, will only have one igniter. That's perfect. Another system that we design inside the avionics team is the ground station. Basically, the OBEC computer, the ESP32, will communicate with an external computer that is located next to the launch pad via RS485 protocol. This external microcontroller will connect to a laptop situated in the but at a safe distance. We tested this to up to a maximum of 1.5 kilometers, so approx 0.7 miles, I think. And the idea is that using this launchpad computer, we can monitor all of the engine and loading parameters and control them via a graphical user interface. This wireless connection is using XP commercial radios, which were already tested. You can go ahead. This is a complete system diagram of the launchpad computer. As you can see, there are various actuators and sensors. All of them connect to the launchpad computer. All of this data is communicated back to the MCC. That's what we call the mission control computer, which is basically an XV-equipped laptop. And this connects to the OBEC computer, the computer inside the rocket, via an umbilical cord that is automatically disconnects when the rocket launches. You can go ahead. This is a picture of the web application that we use to interact with the system. The idea is that we have a simple and quick user interface to debug any of the problems that could occur when trying to launch the rocket. And finally, the ground station, and most importantly, is in charge of igniting the image for the motor. I think that's basically it for the avionics part. We can talk about the launch rate now.
Okay, so the launch rate is kind of quite a standard launch rate. It's just I don't know how it is called. Is I think aluminum truss is the how it is called in English. This kind of tower, and it's set into a steel base that has four legs and is it's just fixed to the ground by a set of fixing assemblies that we design. These fixing assemblies are this anchoring system. That was the word. It just consists in two blades that goes into the ground and are just threaded one onto the other. So we test this here in Argentina, and it worked quite well. So we're using this for anchoring these four legs of the launch rail, and also to anchor four tension cables that goes from the top of the tower to the ground. So right now, this little project, the rocket is almost complete. We think that we have estimated a completion time of 2 weeks. That set us for finalizing or having the rocket ready at May 31st. And after that, we had 10 days to correct minor details until we have to ship everything to New Mexico. Both subsystem testing and computer simulation via CFD analysis were used quite heavily to ensure that everything works. We already have travel plans to Las Cruces. Our university is taking care of that, of airplane tickets and accommodation in Las Cruces. So we're expecting to arrive early, probably 3 or 4 days earlier, in order to test all the subsystems, to assemble everything, and to have everything ready before the competition starts. So we have completed the successful motor static fire with everything, with all the propulsion system integrated. One time with data, the other time without data. The engine has nominal operation, everything worked as we expected to in terms of mechanical integrity and thermal loads. The ignition sequence works pretty well. We also validated the launchpad ACOP, or the standard operating procedure, nitrous oxide filling, nitrous oxide system hydrostatic, and and gas leaks are also tested. Um, and the only thing that we have to test is the umbilical connection from the rocket to the ground system. Well, as I said, we successfully test the hydraulically and pneumatically the pressure vessel. The SRAL computers are already tested. We have to test the COTS computer uh, that we will be doing this next week. We have a shaker, access to a shaker and a centrifugal force machine. So we will be testing that in that environment to assure that all the recovery part is working correctly. Um, we have successfully test parachute deployment, and we also successfully test ejection charts and line cutters, but with the black powder that we have here in Argentina. So we'll have to repeat these tests in the US. So this is kind of the next steps that we will be doing in the next days, next week. Um, Mainly finishing structural parts, just we have to end manufacturing or machining the columns and some parts of the ball base, and also we have to make the deep to deep um, placement of the fins and to polish and paint everything. From the avionics and recovery team, as I said before, we have to test the COTS computer, the recovery computers. We also want to have everything just uh, reorganized again, so we can be sure of everything, all the cable management inside the EV. From the ground equipment, we have to test the XVs, the 900 megahertz XV. We are testing right now with 2.4 gigahertz XVs, which is like the Wi-Fi frequency. So not very good, but it's what we have right now. But we already bought these 900 megahertz XVs that are quite better. So as is a modular system, this test has to be quite simple. Um, we have to do the fin system final integration and the test of the umbilical disconnection. From the propulsion subsystems, we will be doing another static fire just to get data, another data point for the rocket performance, the model performance. Um, the only thing that we have to do in the propulsion team is to optimize the valves to be slightly more lightweight uh, for flight, and to prepare everything to be shipped to New Mexico, which is not it's not something that is quite trivial, but we have to do that. So well, that was this part of the presentation. I know uh, if we have any issues with Meet.
No, I think it's all good.
Yeah.
Um,
Okay, so that was like a short overview of the project. So now we are open to all the questions that you have.
I don't have many questions. It was a great presentation. Rocket looks really nice. Um, let's see. The let's see. Uh, I have I have one curiosity question. You 3D printed your payload sled. What material is that 3D printed in?
Well, right now this is 3D printed 100% into ABS. I mean, 100% infill in ABS. We are, I think next week we are getting a new version 3D printed in nylon. So that will be the fly electronic sled will be 3D printed in nylon, 100%.
Okay, okay, that sounds good. Just curious about it. Let's see. Other than that, your line cutters. You said that you're using wire to hold the main chute together, and then you're line cutting the wire, or
Yeah,
what
Yes.
line are you using?
for the for the main parachute, we are using zip ties for holding the main parachute. I know the word, but
That's
to avoid it from deploy. And the line cutters are a copy of the Piranha line cutters. I don't know if you know that ones. yeah, we're using zip ties.
Could you say the material you're cutting with? Are you cutting?
We're using zip ties to wrap
Oh, okay.
the main
Okay.
parachute. Yeah.
Oh, okay.
We already tested the exact zip ties we're going to use, and the line cutters function perfectly. So
Okay. Okay. Yeah, I was just curious about that too.
yeah, no,
I
maybe I didn't mean to say wire. Maybe.
yeah. I don't see anything else. I think you've got a good solid rocket. Looks like you've got everything under control. So I don't see any problem with you guys flying. Other than that, I'll go ahead and close out your video presentation on the Hero X, and guess I'll see you guys in New Mexico.
Okay, thank you, Paul. Thank you very much.
Uh,
Good to see you.
have you guys already ordered your nitrous?
No, we are in the process. We have kind of, I mean, it's not that easy for us to just to contact to New Mexico. If you have any kind of contact, you know how is the normal process, we will be very pleased to know that. Um,
Excuse me?
okay, sorry, but hablamos si quieres porque...
No, we were wondering if you have any suggestions or if you know anywhere we can get it in New Mexico.
So I will send you I will send you information on that. I had last year they got nitrous out of air gas in Las Cruces,
Okay.
and that's what we're going to try to do again this year. And basically, you contact them and you order it from them, and tell them that you're part of the ESRA group. And what they're going to do is they're going to all their 7 hybrid teams are going to get 7 sets of nitrous, whatever ones you order, what else everybody else orders. They're going to put it all together on one truck with labels on them for who ordered them, and then they're supposed to get them out there the Saturday before the week of competition, and then they're going to drop them off by the pads, and we'll have your tanks when you order your tanks. We'll have your tank sitting out there next to where your pad's going to be, and then you can deal with it from there.
Okay, awesome. Thank you.
I have 2 final questions.
And I also I just got a plan diagram of the site and the control table and everything. So I will be sending that to you guys so that you can see how it looks like actually on the ground, where the pads are at and where the controls are at, so that you know what the setup's going to be before you get there.
Okay, awesome. So,
And
Yeah.
Delaney, you have questions?
Yeah, I have 2. First one is, do you have any final suggestions for us? Anything we should work on over the next 2-3 weeks?
No, you're planning. You know more about what you need to get done than I do.
okay.
It looks like you just have a few details to take care of. So,
Yeah.
so I have no suggestions. I think you're doing great.
Great. And out of curiosity, is that a dog on your lap? We were curious. Yeah, that's a cute dog. We were wondering.
Yeah. She's a Chihuahua.
Oh. Well, I hope she liked our presentation and our rocket.
Yeah, she's all of 2 kilos. She
can be the payload.
Well, so that's all. Thank you,
Yeah,
Paul.
thank you very much.
And see you in Las Cruces, I think.
Yes, sir.
See you there.
Well, bye.
Thank you, ma'am.
Bye-bye.
Bye. Thank you very much.
Yep.